So the next topic that we'll discuss is about artificial magnets. So if you look at it, when you talk about a natural magnet, so the natural magnet is you take this magnetite. So what will happen to this is this will exhibit magnetism, but it will not be strong enough that you can use it for commercial or industrial purposes. So what do we need to do is we need to make sure that this naturally occurring magnet is converted into an artificial magnet, right? So when you talk about the different kinds of artificial magnet, the first one which is commonly used is a bar magnet. So generally what happens is whenever you design a magnet, it is always important that you give color. See, for example, there is something written over here, north and south. But suppose I show you like this and I ask you which is north pole and which is south pole. First thing, you will not be able to see anything. If at all you are able to see also, you will not be able to figure out. So instead what we can do is, if I give you color just as a code, it will be easy for you to identify even at a longer distance. That is the reason why this code is given, color code. So red is given for north and blue is given for south. Second, you can think of a magnetic needle. So where do we have this magnetic needle? Mostly it is used in the compass. So what does this magnetic needle do? So when you say it's a magnetic needle, magnet placed in the presence of external magnetic field will experience torque. So magnet placed in the presence of external magnetic field will experience torque. In the sense, this is there, no. So it is a thin magnetized steel needle having pointed ends and it is pivoted at its center so that it is free to rotate in a horizontal plane. So when it is rotating, no, it will rotate in the horizontal plane. At the same time, it will vibrate also like this. This is something called as dip. The question is, when you look at this magnet, why do we use a compass in the first place? For navigation, right? Yeah, for knowing the directions. So when I say navigation, the point is, how is the pointer able to rotate? Where does it get the magnetic field from? You are not taking another magnet and keeping it closer, no? So how does that happen? It is because of the Earth's magnetism, right? Because of the Earth's magnetism, you can see that it is rotating. But as I told you, no, while it is rotating, it will also move like this, which is called as dip. Okay. So this is also a magnet, but not a very strong magnet, right? Third, you can think of it. So this is a horseshoe magnet because it looks in the shape of a horseshoe, right? So it has the shape of a horseshoe and thus named like that. So there is something else called as a ball-ended magnet. Again, if you see, this also has a color code. What is it? Red is used for north and the blue is used for south. The same logic. If you see all the four, there is a color code that is used. So wherever red comes, it is north. It is understood. Am I clear with this? So this is all about artificial magnets, right? Point is, these magnets exhibit certain basic properties, right? That's what we call it as the basic properties of magnets. If you look at it, we look at them one by one, okay? So when you talk about the magnets, the first thing is, see, here I am taking it close. It is getting attracted, right? So here we are talking about attractive property. So when you talk about the basic property of a magnet, it can get attracted at the same time repelled also. But the main property we are going to talk about is going to be the attractive property. See what attractive property we are talking about. Thing is, when you have a magnet, what kind of particles can it attract? It can attract the iron or the steel particles. So that's how we generally test something. Right, when you take closer to an iron particle or a steel particle, it is going to attract them, right? So when you take a small pieces of iron, cobalt, nickel, etc., when you bring this magnet, see, thing is, you are not going to go and touch it. Here also, if you see, I didn't go and touch it like this. I didn't go and touch it. I keep it close itself. It is automatically pulling my hand. Okay. So when you take it closer to that substance, closer to that particle, what will happen is, so what particles? You can think of heap of iron filings. Okay, iron filings in the sense, small pieces of iron that is scraped out. Right, you would have seen it, it will look like brown color dust. Right. So when you take the iron filings close, the first thing that you can observe is, the ends of the magnet show the greatest attraction. And why is it going to happen? Because the ends of the magnet is going to have the poles. It is going to have the north pole and the south pole, meaning more amount of magnetic substances. So understand two things, okay? One is a magnet and the second is a magnetic substance. So here, the one which contains the north and the south pole is going to be the magnet, whereas the one which is getting attracted is called as the magnetic substance. So here, ion piling is the magnetic substance. So you can observe that more amount of magnetic substance is present near the ends of the magnet, which is basically the poles. Why is it so? Because the strength at that point is going to be very high, right? This is what we call it as the attractive property, right? So these ends where the magnetic attraction is maximum are called as the poles of the magnet. And an important point to be noted is every magnet will always have two poles. Okay, every magnet will have two poles. Am I clear with this? Right? So this is another important thing which is called as the directive property. See, this is a very important property, okay? Listen to this. Start panni. Okay. So the next property that we'll discuss is the directive property, right? What does it state? When a magnet is suspended or pivoted freely, it aligns itself in the geographical north-south direction. The pole of the magnet which points toward the geographical north is called as the north-seeking, and the other pole which points towards the geographical south is called as the south-seeking or south pole of the magnet. Now the question is, I told you that a compass has a magnetic needle, right? So how is it able to know that there is a direction? It is because of the Earth's magnetic field. Now what I'm going to do is, let's say I'm giving you a task where you need to design your own compass. What are you going to do? You're going to design your own compass. Let's say I have this in my hand. Now you don't know what is the direction. You're navigating, you don't know what is the direction. So what are we supposed to do? There is an important basic property exhibited by magnet. What is it? Directive property. So when you take this and suspend it like this, so when you suspend it freely, you're able to see it is rotating. No, there will be on one particular point at which it is going to be stable. I didn't stop it though. See, there it started rotating because of the torsion. It was wound, no, the string had some torque present in it. Due to the torque, it was rotating. Now, if I hold it like this, you are able to see, so what pole is getting directed? Can you see? What pole is getting directed? You tell. So when I hold it like this, no, so this point is actually south. It is south. So it is saying that this direction is the south. Okay. But how will I get a validation? Obviously, I can think of a compass. So generally when you navigate, right, you're not going to hold the compass like this. How will you hold it? This way. So this is because we are going to navigate along this direction. So north, south, east and west. When you look at this, if you observe, can you focus on this? So what direction is getting pointed here? So you are able to see south, right? So if you observe, do you have any, does anyone have a compass in your mobile? You have it? So that side, yeah, sorry, not mobile watch, yeah. Yeah, north, and this side will be south. So what I'm trying to say is, when you suspend this magnet, right, south pole is facing this direction, and that is validated with the help of this compass itself, right? And this property is what is called as the directive property. Cut one. Okay. So did you guys understand what is the meaning of it? No problem. Okay, thank you. Are you clear with this? This is a very important thing. So why is this directive property important? It is important for the navigation, right? Because we should know which is the north pole and which is the south pole. That is why if you remember in the previous chapter also, when we were solving problems, we took north like this, south, we took north, south, east and west, if you remember. So most of the cases you will take it horizontally only. And what north and south pole are you talking about? They are the geographical north and the geographical south. Is the point clear? So just make a quick note of it. So the third property is going to be like poles repel and unlike poles attract. There's no, right? If you take two magnets and suspend them in such a way that if the north pole of the magnet, if the north pole of the first magnet is coming closer to the north pole of the second magnet, they are obviously going to repel, and the vice versa is going to happen for the reverse poles, right? So that's what the third property says. It says like poles repel and unlike poles are going to attract. The fourth point is, when you talk about magnetic poles will always exist in pairs, in the sense, if you take this magnet, okay, if you take this magnet and let's say tomorrow you're going to break it into two pieces, right? So if this is how the magnet is going to be, north and south, if it is broken here, then this will be a small piece, this will be another small piece. Let's say you're breaking it into two equal parts. It is not like that this is going to be north pole and this is going to be south pole. Remember, unlike the electric charges, where in electric charges monopoles will exist. That is, you can think of an isolated positive or an isolated negative. There is nothing like an isolated north pole or isolated south pole. North and south pole in the magnet will always exist in pairs. So this will have north-south, this will also have north-south, but the difference is going to be in such a way that if this has a strength of, let's say, x, right? When you break it into two equal parts, this will have a strength of x by 2 and x by 2, provided you break it into two equal parts. Suppose you are going to break this further. So the ratio according to which you are breaking it, it will change, the strength of the magnet will change in accordance. Is the point clear? Right. And the last point that we need to know is magnetic induction, right? Generally what happens is a magnet induces, right? What happens? A magnet induces magnetism in a magnetic substance placed closer to it, right? This is a magnet, bell pins, okay? We take some bell pins like this. Now, what I will do is, I will take this pole closer to this. Did you understand what happened? Did I touch it? I didn't know. But when I took it closer, what was actually happening? This magnet has a field around it, and that field will start inducing magnetic field in this. That is why there was no physical contact. Try to understand that. So without any physical contact, you can see that it will come and get attracted, because it will use the air medium and start inducing magnetic field inside this. So that I took the south pole closer to this magnet, so it will start generating this end to be the north pole, and it will push the south pole to the other end. So that this bell pin is also starting to act like a small magnet. You can think of this like a magnetic needle of the compass that we thought of, right? And one more thing, it gives you the validation of torque. See, observe what is happening. Observe it clearly. So it is actually rotating and coming. It is not coming like this. It is rotating. So it is experiencing torque, and this is a non-uniform magnetic field as well. Are you able to understand this? Right? This is what we mean by magnetic field is induced. So what will happen if I keep these two in contact for some time, right? And after some time I remove them, you can see that this bell pin will hold the other bell pin even without the help of a magnet. Okay, that is a very important property of this substance, which is called as a ferromagnetic substance. I told you, we'll be learning about three: para, dia and ferro. This is a ferromagnetic substance. It's made of steel. So ferromagnetic substances have an important property associated with it called as retentivity. In the sense, they can retain magnetism. Are you able to understand what I'm trying to say? So they can retain magnetism. Based on this only, we divided the magnets into two types. One is a soft iron core and a hard iron core. If you remember in the previous chapter, when we discussed about galvanometer, what is the core of the galvanometer made up of? The soft iron core. And this is the reason. Because when you talk about an iron substance, it can have magnetism retained within it. What is the objective of a galvanometer? Not to retain magnetism. The objective of the galvanometer is only to show you current is there or not. So that is why you choose the magnet accordingly. Are you able to connect the dots? Right? So coming back to this point, it says a magnet induces magnetism. So it's like this: magnet induces magnetism in this, In such a way, if you take the south pole closer to this will become north pole and this will become south pole, even without physical contact. Magnet, magnetic substance, right? This phenomenon is called as magnetic induction. Why are you using the word induction? Because no physical contact is there. You are not rubbing one against other. You are actually taking one closer to another, right? When the north pole of a powerful magnet is placed close to the soft iron bar, the closer end of the bar will become south pole. That's what we saw, no? Right? Or else the attraction will not take place according to the third property, right? And the farther end is going to become the north pole, right? As a result, the magnet is going to attract the iron bar, and this induction precedes attraction. In the sense, the first property we saw, no, the attractive property. So this concept is also supporting the attractive property. It is supporting two things. What is it? One is the attractive property, and the second is like poles repel and the unlike poles attract. So all the properties are actually directing towards only one thing. Am I clear with this?